Hello everyone. Thank you for joining this session. My name is Ray. I'm a developer advocate for Google Cloud Platform. What that means is that I love to bring some of the best technologies to developers all over the world, but I also love to get your feedback on our technologies and how you're using Google Cloud. So if you have any questions and feedback, you can find me on Twitter, which is @Satanism. Recently, I worked on a couple production projects to run and operate Java-based microservices in the Kubernetes environment. I spent more than half a year on one of these projects, and I'd like to share some of my experiences and practices that I learned. The project was to help an alphabet company to adopt cloud. So instead of using Google's internal platform with Google's internal frameworks, the team had to use a public cloud and many open source components like Kubernetes, Spring Boot framework, and more. And to do this, we formed two different teams. One team to focus on the cloud infrastructure and many of the DevOps concerns, such as provisioning the infrastructure, CI/CD pipeline, monitoring, alerting, and security, and more. The second team focuses on the application development and the business requirement. But keep in mind, this is simply because the teams are very familiar with Google's internal technology, but there is just a lot to learn when it comes to the open source world and cloud. And we needed to divide and conquer so each team can focus on a smaller set of problems to solve. Even though we have these two focuses, the teams actually operate as a single team. And we discuss business requirements together, architecture needs together, and operational needs together. And ultimately, the application team will also be responsible for taking over the operation as well. This is the high-level view of what we implemented. The entire application is composed of a set of microservices. All the services are containerized and deployed into a private Kubernetes cluster that only has internal IPs. For service-to-service communication, we adopted Istio, the service mesh, that can help us not only to route traffic, but it can also add resiliency to our services by transparently configure retry rules and circuit breaker rules. Most importantly, it can establish secure mutual TLS connections between our services. In the front, we have a cloud HTTP load balancer that can route traffic from the public endpoint into our cluster and through Istio to our backends. The production environment is meant for public access, but we don't want random users to find and use our non-production environments. And to secure our non-prod environments, we're using Google's identity-aware proxy. It is enabled purely by just configuring the HTTP load balancer, and it can automatically add authentication authorization capabilities without us having to change the code. All the services are being monitored, and we have set up alerting rules for common service level objectives like latency and availabilities and more. The application metrics are collected using Prometheus and graphed with Grafana. And Istio, the service mesh, also provide a lot of the monitoring metrics and dashboards out of the box. It definitely saved us quite a lot of time simply by using these out-of-the-box configurations. And finally, to complete our security parameter, we also want to control all outbound traffic, and we are doing this through Istio's egress gateway and secondary through our cloud ANT gateway. And so that if anyone happens to infiltrate the system, they cannot extrafit the data. This is a pretty common architecture, but I can tell you the road to this was not easy. Rather than talking about how we actually configured each component, I'd like to share with you the processes and lessons learned that we went through on how we decided to adopt and implement these technologies. First, when I joined the project, the team already had set up a Kubernetes cluster, a database, and more in their development environment. On Google Cloud, this is super easy to do using our web console. However, the team quickly discovered that this is not a scalable way, nor a consistent way to provision higher level environment. It's simply impossible to figure out all the clicks and the values that we entered into the UI. So even if you documented everything, the process itself is still not automated. So the first thing that we did was to move to infrastructure as code and adopt GitOps practices. We provision everything to Terraform, and we check in all the Terraform files. And by everything, I mean all the cloud infrastructure like Kubernetes cluster, Cloud SQL database, and all the network configurations. But we also make sure that all of the Kubernetes components like Istio and other components that's necessary for an application to operate, minus the application itself, are all provisioned when we set up the new environment. In the end, when we produce a new environment like staging or QA, our application developers can simply deploy their application into the Kubernetes namespace, and everything else is ready to go. This process will require us to produce a configuration file for every piece of our infrastructure, whether it's in Terraform or Kubernetes YAML files. There are lots of YAML files. While YAML itself is getting a lot of complaints recently, in reality, these files really help us to codify the environment that we want, and our provisioning process is now consistent and repeatable. For Kubernetes, some people like to use a tool like Helm to install components like Istio. In the earlier version of Helm, there's a server-side component called Tiller that will take a small set of value configurations and expanding those configurations into the fully hydrated configuration and deploy it into Kubernetes. To use a high-level abstraction tool like this requires a lot of trust. What if Helm interpreted the value differently than what we intended? What if there's a bug in the server-side component? It will become a little bit more difficult to troubleshoot. So rather than depending on this hidden layer on the server side, the team overwhelmingly prefers the client-side template generation. So even if we are using Helm, we always check in the fully generated or hydrated YAML file. The initial checking may result in a file with hundreds or thousands of lines of YAML, but the incremental changes become much easier and obvious when you just see the diff in a pull request. Once the files are checked in, whether it's the application code or infrastructure configuration, we will then kick off the CI/CD pipeline. The CI/CD are in fact two stages. For an application code checking, we'll kick off the CI pipeline, which will build and test the application, apply the code quality checks, then produce the container image. And rather than deploying the container image directly, the last step of the CI pipeline is to update the Kubernetes YAML file to point the container image to the latest version. Once the YAML file is updated and checked in, then it triggers the CD pipeline to run. And at this point, the CD pipeline is really just applying all the configuration files. So previously, if there are infrastructure configurations that needs to be applied, that can also be triggered, the CD pipeline. But when the code change happens, once the last step of the CI pipeline updates the manifest, it will trigger the same CD pipeline, and it will then deploy the newest version of the container image to the cluster. When we started off this journey, there were definitely a lot of cool and new technology on our minds. For example, CQRS and event-driven architecture sounds very scalable. Maybe we need that. Everyone's talking about that and Kafka. Do we want to have Kafka in our system? Kubernetes and Service Mesh are really, really cool, and we must have those, right? And the list kind of piled on. What I don't want everyone to do here is that after this talk, that you go back to the very first diagram and say, hey, let's implement everything in this diagram. That's not the best practice, nor the lessons at all. When we are faced with these technology choices, we always go back to the root of the business need and the requirements. What do we really want to achieve? What do we really need? We needed to evaluate each technology for its maturity and does it actually fulfill our requirements, and come up with an informed decision collectively as the team. Unless you've been through the productionization a couple of times, it's very difficult to adapt everything in one big bang. So instead, once you have an idea of what architecture you want, then start to think like building a house and adopt the foundational stuff first, and then build on top of that incrementally, step by step. When considering pros and cons, there are many dimensions to consider, like maturity of a technology, how easy or difficult is it to operate, do we have the skill sets to run it in production? If not, how long would it take to ramp up? Many of these factors are not simply based on the superiority of a technology, but based on the current reality of the team. For example, the very first question the development team asks is, where do we store the code? Do we put them in a monorepo or a multi-repo? To some, this is a fundamental existential question, a philosophical question of, do you want to build a distributed monolith or a true distributed service? Because in a monorepo, you might tie the microservices releases together, which essentially make the release cycle as slow as a monolith. But the answer is, it depends. There are many pros and cons to either approach. For example, a monorepo is easier to get started. We only need to build a single CI/CD pipeline to start with. If there are common libraries to share, it's also much easier because it's all in the same project. The initial velocity of a monorepo is much faster. On the other hand, multi-repo has many benefits, especially when it comes to decouple the services. But then we have many other things to consider. For example, we have to have proper infrastructure to support it. We now need to be ready for multiple CI/CD pipelines. What if a CI/CD process changes in the middle of the project? We then have to go back and fix all of the pipelines, which is not something that we wanted to spend time doing initially. And to share a common library, we then need to host the library in a Maven repository. Then the question is, would it be something like Artifactory or Nexus or somewhere else? We now have to spend time evaluating new technology choices. But the worst part of it is that even if we picked one of the technology, then we have to operate and monitor this additional piece of infrastructure. Ultimately, we chose to use monorepo because the reality is the team was small, and it's not like we have many different teams releasing many services every day. It's just one team with a couple of people who are mostly Google engineers who are already familiar with the monorepo. So we simply don't have the bandwidth to really set up a proper multi-repo infrastructure. And so we base our decision on the current reality and the needs of the team. However, we anticipated change. The decisions that we made yesterday were the best decisions we could have made based on yesterday's reality. But the reality changes over time. The team may grow in size and skill set. The technology that was not mature yesterday may have matured today. Every choices that we made in the past may be different if we were to reevaluate and make the choice again today or tomorrow. So it's very important that we don't lock ourselves in one choice and always anticipate things to change over time. For example, even though we chose to use monorepo, we anticipated that we will outgrow it one day and move to multi-repo instead, especially when the application grows in complexity and when we are better staffed in the future. So even though we are using monorepo today, we make sure that we design the code repository in a way that can be split in the future. Every service, for example, is self-contained, and we avoided circular service dependencies. And if we need to reference a common library, we make sure that the dependency reference can be easily reconfigured to point to a Maven artifact rather than the internal codebase. We also made sure services are decoupled so that rather than sharing the client library code and some business logic in between, except through the common libraries, when I need to code on the service, I need to use the interface definition file, like a gRPC proto file definition, and then generate the client-side stub for it, so that my only view into another service is by these well-defined protobuf definitions or service definitions. And luckily, this is easy when you're using technology like gRPC. And because we anticipated to move to multi-repo, as the team grew and new teams were formed to take ownership of some of these services, we were actually successful in breaking those services out of the Mono repository into its own repository. Lastly, I don't know if anyone had this experience where you are kind of wandering in a high-rise and then you entered into a stairway via a door and then you unknowingly close the door behind you. And all of a sudden you realized the door cannot be opened again and you cannot go back. And now the only way that you can get back into the building is to climb all the way back down to the first floor and then take the elevator back up. This actually happened to me many times, and it's kind of notorious in some of the Google offices. And you want to avoid these one-way doors as much as possible during implementation. This can definitely happen. If you didn't design your Mono Repo well, for example, then it will be really hard and difficult to migrate some services into multi-repo in the future. And some of these one-way doors are easier to enter in the cloud than you think. For example, if you misconfigured a cloud resource, like you created a Kubernetes cluster with public IP address, and now you need to make it a private IP cluster, it is not a simple switch anymore. You may actually have to destroy the existing cluster and then recreating it again. And sometimes you might discover some of these things are very late in the game, right? So for example, we provisioned Istio with the default configuration and it worked really well all the time. Until when we were towards the very late stage where we are trying to lock down the cluster for production and adding more and more security policies. And then we discovered that some parts of Istio required escalated privileges. And to fix this, we have to reconfigure Istio to use a different way of routing traffic using CNI. And to do this, we may actually have to go back to the beginning and then reinstall Istio, reconfiguring it, and then now we have to retest the performance and everything else, right? So you want to avoid some of these things as much as possible. Some of them may take experiences to avoid, but in general, if you adapt carefully, incrementally, and anticipate change, you can avoid many of them. So far, we discussed a lot about infrastructure and the process of how we adopt technology. Now let's talk about microservices. When we design our services, we focus on the software design and software architecture itself. And it has mostly nothing to do with Kubernetes. In fact, if you design your services well, it should be able to run in any environment, including Kubernetes or somewhere else. Because the environment keeps on changing year after year. In fact, in the past, our applications may be running in the VM, and then there was the era for platform as a service, and now we have Kubernetes that's running the applications. And tomorrow, it could be something completely different. But in all cases, your application remains mostly the same. It needs a way to start, and then it listens on a port, and it responds to some requests, and finally shuts down, hopefully gracefully. And for the most part, rather than designing your software just for Kubernetes, you should be designing these services by following the 12-factor application principles. Everyone here should be implementing the 12-factor apps. If you haven't heard about this, you should definitely check it out, because many of these principles have proven to be timeless, and Kubernetes can run 12-factor apps very well. And it is rare that I find any services that implements all 12 factors. But everyone here should have at least one factor, which is checking your code. Okay, so everyone here should at least have a one-factor app. But there are many other factors that are also important, and I'll call out a few here. For example, you want to make sure that your application can be configured from an external source, like using an environmental variable. As Java developers, I know that we often hardcode property files that cannot be overwritten, and so we have to change and rebuild our application. And it's important that these configurations can be externalized or can be configured from an external source. Your application or services should be stateless, and so that it can be scaled out just simply by starting another process. You cannot do this easily with a stateful application. And finally, it should handle graceful shutdown so that it can do the necessary cleanup when the platform indicates that it needs to go away. Right? And all of these attributes are important for any successful microservices and definitely can benefit from running in Kubernetes, because Kubernetes can take advantage of many of these attributes. Sometimes I hear people's dreams of having a local development environment that is exactly the same as production. And so they try to set up local Kubernetes environment that is exactly the same as production. And I don't think that worked in my experiences because production is not ready yet. No one knows what production look like until it's gone live. So you don't want to wait until production environment is ready before you start developing in your local dev. They will never be the same. And secondly, production is hard. There's a lot more constraints and complexity in a production environment. And this is usually why some software just don't work in prod the first try. And would it be nice to be able to capture some of these issues early, some of these incompatibility and differences in environment? Sure, definitely. But we can probably do that in QA or staging environment. That is definitely more like prod. In fact, staging should be exactly like prod, right? But having a lot of the production complexity in a local environment is going to slow down development velocity significantly. You're going to be running a lot more components locally, which will slow down your machine as a whole. But it also adds a lot of complexity. Like if you imagine using Istio locally and you run into an issue with a service mesh, now the developers have to troubleshoot these issues, and these issues can be difficult to troubleshoot, right? And this will definitely slow down the development velocity. So for us, we focus on the software design, the 12-factor app principles, and we make sure that everything can be tested independently from each other, and also they can be tested and developed locally even without Kubernetes in the first place. Because it's really just a service that listens on the port, that responds to a request, right? And it can be shut down gracefully. And you can test all of these things without having a full Kubernetes environment. And there are many different techniques to be able to test your applications locally, all without Kubernetes at all. First of all, you need to have really good unit tests, and then some integration tests. And to do integration tests with another service, mostly you may have to depend on some kind of stub so that you can at least make sure that you can simulate the service behaviors. If you want to be more complete, you can use something like WireMock that can then emulate and simulate your requests over the wire, and then getting the response. One of my favorite tools to use though is called test containers, because sometimes you can containerize a service, a stub service, or like simply the database. You can run a database container. And what test container can do is that during the testing cycle, it can automatically start the container for you and set up all the wiring, and now your tests can use the containerized services. And then once it's done, it can shut down the container for you as well. And this is all tied into the existing unit testing frameworks. So here's an example of a test container configuration that first you add the POM XML with the dependencies. And then you can add the test container related annotations into the unit test itself. In this example, I am going to start a Postgres database container for my unit test. And now if I'm running the test, it will automatically start the container, and then my test can now connect to my container locally as well. But sometimes after we run all the tests, we still want to see everything working together. Seeing is believing, right? And for this, we mostly relied on the auto push or integration environment, where all the latest code checkings is CI/CD'd and pushed into this environment, so we can log in and see everything working together. Or sometimes people just really want to see everything working together locally, then they can run local Kubernetes environment, but minus all the production complexity. So for example, we don't run Istio locally for all the developers because Istio may be harder to debug, right? And we don't want to ask every developer to become an Istio expert on day one. And so we don't want to have anyone spending a lot of time debugging Istio issues. And also Istio components might take more resources to run, and we also don't want to hog the machine resources when it should be spent for application development purposes. We can add Istio later as long as the application conforms to the contracts. When your service is ready and it can finally be deployed into a Kubernetes environment, then you need to create the container image and write the Kubernetes deployment YAML files. A good friend of mine from the community, Matt Rabel, he works at a company called Okta. And he always say that friends don't let friends write authentication because you need authentication everywhere. It's mundane and repetitive to do it, and it can also be an error-prone process to write your own authenticators. So rather than doing this yourself, just use a service, for example. And I'll also say that when building a container image, friends don't let friends write a Docker file. Because Docker file also needs to be everywhere, it can also be mundane and repetitive. And writing a good Docker file is also error-prone. And there are many tools out there that can help you automate the container image creation process without you having to write a single line of Docker file. For example, you can use a tool called Jib. Jib is a Google project that's specially designed to containerize Java application. For example, here I have a Spring Boot application. And in the build file, I can simply add a Jib plugin. We have plugins for both Maven and Gradle. And then you can just simply build it and say Jib build. And what this will do is to allow the Jib plugin to analyze your source and your build file and produce the most optimal container image with the right layering, and then pushing the layers that has changed into a remote registry while implementing many of the best practices that I cannot actually talk about today just because there are just so many of them. And just by jibbing the application, you're much closer to a container image that's production ready. Another alternative is cloud build packs. While Jib is great for Java applications, you can use a cloud build pack to build your application, whether it's written in Java, JavaScript, Go, or Python, or any application that's written in a supported language. The build pack can turn these applications into a container image with the best practices as well, or without a Docker file. Similarly, you don't want to rewrite the Kubernetes YAML file over and over again either. To avoid this, you can also use some tools to generate it. So for example, kubectl command line has the built-in command that allows you to generate a bootstrapped deployment file or a service file that you can then later enhance. Or you can also try a tool like Decorate. It's an annotation processing tool that can analyze your application and produce a fairly good YAML file for deployment just through annotation processing. So in this example, I can add the Decorate library into my Spring Boot application. And this application happens to also have a Spring Boot actuator component so that it can automatically install a health check for me. And once you build the application, Decorate will automatically generate the YAML file. And if I open this up, you can see not only does it have the basic configurations, but it also has all the health checking information as well. Now you can deploy the entire application into Kubernetes. However, when you do discover some issues with the running app, you may need to go back to the source code, recompile, and then rebuild the container image, and then redeploy. This is called the development loop that you may have to repeat over and over again, but the good news is that you can actually automate it. And we have a tool to do just this, and it's called Cloud Code. It's a plugin that works in both IntelliJ IDE and VS Code. So in this Spring Boot application, I can enable Kubernetes support. This will then generate a Skaffold YAML file. And you can use this file to configure what you want to build and which Kubernetes files you want to deploy. You can see that this file is already pre-configured to build my application using the Jib plugin because I already configured it. And down here, you can see that you can select the Kubernetes files you want to deploy. Then you can go ahead in the IDE and develop with Kubernetes. This will then rebuild your application, build the container image, deploy the Kubernetes YAML file, and even automatically establish a local port forward so that the local port 8080 is now connecting to the load balancer within Kubernetes. And so that your request to your local port is now routed to your backend. And you can also see that the logs are automatically streamed from the Kubernetes cluster into your local console. So this actually makes running an application in Kubernetes feels a lot like it's running locally. If you change the source code, it will detect the change and then rebuild the container image, redeploy, and do this automatically so you don't have to do this manually yourself. You can even run this in debug mode, in which case it will automatically enable the debugger port and connect your IDE to this remote debugger. You can then add breakpoints to your source code. And when you test your application, it can trigger the breakpoint, and now you can step through the code as if it was running locally on your machine. Finally, the debugger can also do code hot swap. So you can make trivial code changes without having to redeploy at all. Finally, when we do promote the application through the different environments, like from the dev environment to QA to staging, we need a way to change configuration so that it's specific to the environment. For example, the username password could change, or the number of instances in QA and prod may be different. And we don't want to duplicate the entire Kubernetes YAML file over and over again either. That will be repetitive and error-prone. And this can be achieved through using some kind of templating tool. And we have a tool, and we use a tool called Kustomize. And this is how it works. So first, create a new directory. Let's call it Kustomize. And then we need another directory here with a base set of files that we want to customize for different environments. And these files are meant not to be duplicated over and over again. So let me just copy the base set from my original files here. Okay. And then what we can do is to add a customization file. So let me go ahead and add that, customization.yaml. And this has a specific kind. And once you have this customization file, then you can start enlist the resources or these files that you want to be able to customize later. So for example, in our case, I'm going to add the deployment YAML and the service YAML. And so far, everything feels like it's normal. It's just a regular set of Kubernetes file. The only difference now is that if I go to the base directory, I should be able to do something like customize build. And what this will do is to read the customization file and then combine everything into a single output. And then you can pipe this output directly to Kubernetes to deploy everything in one shot. But now let's do some customization. Let's say for development purposes, I only have one single copy of my application. But in QA, maybe I want to test with 2 instances instead. So let's go ahead and create a new directory here called QA. And then, rather than duplicating both the deployment and the service file, let me just create the customization file again. And rather than explicitly stating which files I want to customize, I can just customize the base. So this is almost like inheriting the base configurations. But in my QA environment, I want to apply some changes, and these are patch files I can add that will then be merged with the base file to make these different configurations. So for example, what I can do is to add another file. Maybe I want to scale things out. So I'll call this scale replicas.yaml. In this YAML file, rather than duplicating the entire deployment configuration, what I can do is to just copy the top of this, which is really the key. The key is the API version, the kind, and the name. And I don't need anything else. And then I can just focus on the key values that I want to change for this particular configuration rather than duplicating the whole thing. And so here in the replicas, rather than having 1, I can change it to 2. Back in the customization, I can instruct Kustomize to read this specific patch. So this is going to be able to use what we call a strategic merge. And what I'm going to do is to merge in this different patch, okay? Now, if I go back to my console, and if I go to the QA directory, okay, and again, if I do a customize build, this will actually read the customization file, inherit everything from the base directory, and then apply this patch. And now my application should only should have like replicas set to 2. And now I can actually just apply this directly to Kubernetes. And the newer version of the kubectl command line, I can actually say kubectl apply -k, and this will actually execute the customizations as well. But since we're using Cloud Code and Skaffold, what I can do is to tie everything up together. Okay, so here, rather than deploying directly from the Kubernetes manifest, I can deploy instead from Kustomize. And which files do I want to deploy? Well, I'm going to deploy from Kustomize base, for example. And now, if I were to develop on Kubernetes, then it will use the base file that I'm using for development purposes. And then if I need to deploy this into QA environment, then I can apply the QA set of files. In in Skaffold, the last thing that we can do is to also specify different profiles. So for example, maybe you want to test out a different profile or a different set of configurations in Kubernetes. And what you can do is to add a new profile, let's call this QA. And then in here, I want to use Kustomize to do the deployment as well. And for the path, I can say, you know what, for the QA profile, rather than using the base, I'm going to use the QA directory. Okay? And now when you are doing the develop or debugging on Kubernetes, if you go back to the configuration, to the UI here, and you should be able to see the deployment profile, and you can also see that now you can choose a different profile to use, and you can apply this. And now if you run it in this developing Kubernetes mode, then we are going to use the customized configurations just for the QA. The last thing I want to talk about is that now your application is designed with 12-factor app. Remember what I talked about earlier about graceful shutdown and health checks. These are your contracts between your application and the orchestration environment that you're running in. So today, we're running everything within Kubernetes. Then we have to ask, how does Kubernetes know that your application is up to running and that your application is in trouble? It might need some help to restart. And how does Kubernetes tell your application to shut down gracefully? So these are the basic application contracts that we can finally get to in order for your application to run inside of Kubernetes successfully. The first contract is how much resource is your application going to use, so that Kubernetes can effectively schedule your application onto a computing resource that has enough resources for your app. So this is called the resource request and resource limit. So the request is basically the bare minimum, the minimum resource that your application actually need. Okay, so let's add a request here. And what is the minimum CPUs that we need? And this we can say the minimum CPU is 2000 millicores. What millicores means is that this is 1/1000th of core. So 2000 1/1000th means 2 cores at the minimum. For a small application, maybe you can start off with just half a core, and that will be 500 millis. And then, how much memory does your application need at the minimum? For a Java application, every application differs, but for this very small application, I'm going to say I need at least 256 megabytes of memory. Now notice the M here is the big M, is the capitalized M. If you use the small m here, that will be 256 1/1000th, right? And that will be less than a megabyte, and that's not what you want. And the other thing that you can add is the limit. Limit is how much you can use at maximum. Okay, so for example, I can say for the maximum CPU that I want to be able to use is 2 CPUs. So here I can actually say 2000 millis, and the maximum number of the amount of memory that I want to use is maybe 1 gigabyte. Or you can make this a little bit smaller and make it 512 megabytes instead. Okay. Now, the one thing to keep in mind is that CPU is a compressible resource. What that means is that if you exceeded the CPU limit, then we will just throttle you. We will slow your application down so that you don't consume that much CPU cycles. Memory, however, is not compressible. What that means then is that if you exceeded the memory limit, then Kubernetes will go ahead and remove your application. And this is where you see OOM killed error message. The next contract is about how Kubernetes knows that your application is up and running and ready to serve. And there are two different checks for this. There's a liveness probe and a readiness probe. The liveness probe is the one that checks whether your application is alive. So if you fail the liveness probe, what that means is that Kubernetes will kill your application and try to restart it. It assumes that by restarting your application can actually recover. The readiness probe is telling Kubernetes if you are ready to serve. Why would your application be alive but not ready to serve? Well, maybe you are starting your application is alive, but you're trying to pre-warm up the cache, preloading some data, so it's not ready to serve. Okay. So your application could be alive and not ready. This is important later when we get to graceful shutdown. But to implement this, you can use the liveness probe and the readiness probe. Now, we actually have an example of this earlier where we generated the configuration, right? So in this case, using Spring Boot as an example, we can use some very basic endpoint that only returns 200 all the time, like here with actuator info, and we can use this as the liveness probe. And then maybe we can use the health check as the readiness probe, because our application is not really ready to serve until we have all the connections to the backend. One thing to keep in mind is that your liveness probe should not depend on any external resources. Sometimes people put a liveness probe that checks whether the backend database is live. And that is problematic because if your database is down, can Kubernetes fix your application by simply restarting your application? And the answer is no. And if you actually made your liveness probe this way, you may actually cause very bad cascading failures, because if your database is down, Kubernetes is not fixing your database, it's restarting your app, and your app will be restarted continuously until it cannot recover anymore. And if you have other services that depends on this service as well, and these other services also uses your service as a health check, then those downstream services will also be restarted. And none of these things will help you to recover. Okay, so be very careful with these two configurations. If anything, you should always have the readiness probe at all times. The last contract is how Kubernetes will tell you that your application needs to shut down. And it will tell you by default using the SIG-term signal. And once you receive the signal, you're supposed to finish all of your in-flight requests and shut down. However, during this time, Kubernetes might still be sending you new requests because your application may still indicate that it's ready to serve. Okay? So the first thing that you should do once you receive the SIG-term signal is to start to fail your readiness probe. Once your readiness probe is failing, then Kubernetes will stop sending you new requests. During this time, you should definitely just finish up all the in-flight requests and transactions. And once that's all done, shut down the application. Also, by default, Kubernetes will give you some time to shut down, like 30 seconds or so. If you exceeded that time limit, then your application will receive a SIG kill instead, and it will just be gone. If your application takes longer time to shut down, then you should adjust this configuration. It's called the termination graceful period. You can increase it so that you have more time to shut down. And that's it for my presentation. I hope you enjoyed the content. If you have any questions, you can find me on my Twitter, which is @Satanism. And you can find a lot more other information in my collabs and workshops that's available on my site on satanism.me. Thank you.